we've been discussing the flows in porous media recently. Right now, I want to add something to this topic and explain how you can model the heat transfer in porous medium. Like recently, we've given a couple of examples where porous media can really be porous in their microscopic structures, but porous media are generally very often are a very often adopted concept in flow simulations to deal with structures that have some permeability. Well, combustion of the biomass or something like that. In its structure, probably not really a porous structure, but if you stack plenty of different plants, pieces of wood, or whatever else, then how do you represent it in the simulation? Actually, by assuming that it's porous zone. So let's imagine the following example. Heat transfer in porous media. Let's imagine the following situation. You got some cross-section of a channel, and the channel is full of such fins. So is the symmetry. And I don't want to make the picture more obscure, but let's imagine that like you've got the next pair of fins here on the left. Like it's really filled with these fins, and you've got flow that enters from this direction and goes through the whiteboard. So this vector could represent the flow. The question is, you know everything about the flow. You know the volumetric flux. You know what the temperature of the flow is. So we do not want to focus on the flow right now, but what we want to focus on is the heat transfer in the porous medium. What can it be? This can be like radiator of a stirring engine, like, or maybe heat exchanger. Heat exchanger that I think in the stirring engine you want to retain some thermal energy of the gas when it flows from one cylinder to the other, but then you want to take it out again when it goes back. So can you represent it by the porous medium? Yes, you can. How do you represent the heat transfer in the porous medium then? And let's make this example. And let me draw just a representative portion of this geometry. I will cut something like that. So if we zoom it in, you can imagine, well, with certain amount of simplifications that I do on purpose, that it's something like that. And let's not play with the details right now. For whatever reason, let's assume that this dimension is 4 millimeters. This one is, no wonder, 3 millimeters. You very well know why. And let's assume that the thickness of this metal sheet that was used to create these fins is 1 millimeter. And the first question is, what's the porosity? So what's the porosity? Well, let's calculate the surface area of this square. It's like 4 times 3 times 2, because we've got two rectangles. So it's 24 millimeters squared. Let's calculate the surface area of these fins. What is it? It's like 1 millimeter thickness times 5, exactly, times 2 fins. Obviously, I want to show you the procedure how to generate the, okay, or maybe one more comment. What we are trying to do is we are trying to develop such a heat transfer model that will hold for the porous medium, but we can solve it by our numerical methods using standard heat transfer equations. So basically the diffusion or advection equation, or diffusion with the heat source. So that's what we are aiming at. So what we need to do is we need to develop ways to calculate the resultant thermal conductivities in each direction for such a structure. That's the first step, because obviously lambda of the material is not the resultant lambda of such a porous medium. Additionally, this material will certainly have two different thermal conductivities in two different directions. It will differently conduct heat. That's the first part of the example. The second part of the example is that we need to account for heat transfer between this flow with temperature T and some local temperature of the fins at the given point in the geometry. So these are the two things that we want to do. And okay, let's come back here. It's, well, 10. So the porosity is the proportion of what to what?
10 to 24.
10
to 24.
No.
Empty space. Okay, yeah.
Porosity represents pores.
Yeah.
So pores, it's 14 by 24. That's already good. And let's calculate the resultant thermal conductivity in this direction. So let me call this direction X, the other Y. And right now, let's imagine if we define Dirichlet boundary conditions here and here, so we will be generating heat transfer in this direction. So let's try to write such an equation. Total heat transfer, total heat flux would be proportional to lambda x, that we do not know, times or minus, but we can say we are interested in magnitude, really, times the temperature gradient times surface area. Okay, so let me do that. That is something that we want to represent, assuming that we've got porous medium with some averaged parameters. What happens in physics, in reality, it happens a bit differently. Namely, we know that if we keep this boundary at the temperature of, let's say, 1, this one at temperature 0, what will happen in reality is that we need to we will have the following heat transfer. Well, first, we've got two fins, the bottom one and the upper one. Then times thermal conductivity of the material, of the metal sheet that it's built of. Times, well, okay, temperature difference is 1, divided by length is 5, and times surface area, so basically thickness of each fin, well, if you prefer, times the dimension in the third direction, but we can clearly omit that. It's something like that. Here, how do you represent the temperature gradient? Again, it's 1 divided by 4, distance from one boundary to the other. What's the surface area? Well, for the averaged case, it's obviously 6. And these two things must be exactly the same. So let me write that. It's not, it's yeah. So lambda x would be 8, 30 lambda, which is 4/15 of lambda.
How did we change the temperature gradients in 1/4?
Because you want to represent, assuming that you've got the porous medium of some averaged parameters, what you want to do is you want to derive such a lambda x that will represent the heat transfer as it wasn't a porous medium, but as it was like solid. So the distance between this boundary and this boundary is 4. And this 1 comes from the fact that you're keeping this boundary at the temperature of 1 and the other boundary at temperature 0. Okay? In this case, it's exactly the same, but the path for transporting the heat is longer, so it's got 5 millimeters. Well, do you want me to do the same example in the other direction?
Yeah, maybe we can do it in another direction with some different temperatures.
Okay, let's do it then. So in the other direction, maybe under color. In the vertical direction, the magnitude of the heat flux will be lambda y times, again, the average quantities. Then we've got, let's say, this boundary is now 0. This one is 1. The distance is 6. The temperature difference is again 1 times surface area. Surface area is 4, right? The real case would be that if you want to conduct energy from here to here, then the total length of the path is 10. So you've got real thermal conductivity of the material. Temperature difference is 1 divided by 10 times the surface area is just 1, because how it happens in reality, the thickness is just 1, right? Again, these two must be equal to each other. So 4/6 lambda y equals 1/10 lambda, so lambda y equals 64, no.
No,
640, so 3/20 of lambda. And you can clearly see that one is approximately that. But clearly that one is approximately something like that. Well, it's not approximately, it's equal to 1500. So you can clearly see that you're already, you need to treat your porous medium and the heat transfer as heat transfer in the orthotropic material if you want to replace really representing the structure of the material by some averaged model of the porous medium. Tim?
Can you explain it again? What's the difference between magnitude and the lambdas also?
I wasn't very, formal in the. It's Q that you will see in porous medium.
It's the average Q over this whole rectangle.
Yeah, I think it is worth saying also that we are assuming that the air heat conductivity is so low that we can assume that it's vacuum.
That's true.
And then it just playing with geometry.
Yeah, so here when the heat is transported at the y direction, you need to go through all two plates. So the total length would be
Here, 5. Again, 5.
yeah. In the previous
10.
example, you had two plates that transported parallel the heat. So
And this one is, so to say, heat flux, really. Because how the physical mechanism is that you need to, okay, the heat transfer will start here with temperature of 1, and will be dropping here and here, and you can only use the surface area, basically the thickness of the fin of 1 millimeter to conduct the whole heat by this path, along this path.
Why do we do it along this path?
Because there is no other way for the heat to move. It can.
Why does it move not from left to the right because the temperature is higher?
Because we are assuming that the air can be omitted in this case, so the only way for the heat to move is through these metal fins, and we ignore the air because heat conductivity.
Or once again, why we are doing this intuitive, like this derivation process, because we want to represent porous heat transfer in porous media as in every solid. So we want to derive such material coefficients that will give the same results in our simulations that real heat transfer in a porous medium of such a structure would give. So we are completely arbitrary, assuming that, okay, let's imagine we've got the temperature gradient in this direction to calculate our lambda y coefficient. And then let's assume that we've got temperature gradient only in this direction to calculate the thermal conductivity in the x direction. And air is assumed to be adiabatic, like it does not conduct heat, and that's very, very often true. Like the heat conduction is 0.025 compared to any material to any metal, which would be in the order of 100. So that's really nothing. So that's the first step. What's the second step? Yeah, but do you remember our equation? The equation is that we've got, let's say, I will skip the convective term because we've got no convection if we're representing the solid. But what we have got is we've got lambda times temperature plus exactly. Exactly. You need to modify the density and temperature, density and heat capacity properly. I think it's you only need to average this product, so you need to lower the density. So so to say that your representative element of the porous medium has got the same mass as your metal sheet that is enclosed within it. So you would be lowering the density. But if you do that, then CP should stay the same because you simply need to have, because you still have got this material that is less dense in your simulation, so to say. We have already gone through that, but we still need to derive the proper formula for the source term. Because if you've got the flow that is moving in this direction, you've got heat conduction in the porous medium, in the solid part of the porous medium, then you need to couple the fluid flow across the heat exchanger with the temperature distribution that you will be solving for in the solid structure. So the heat transfer at the interface between the solid and the fluid will be clearly represented by the heat source for the solid part. And again, do not be misled by what we've been discussing previously, that at the solid-fluid interface, you don't impose the boundary condition. We don't impose the boundary condition in such a case where you represent in your simulation with within the same domain and with the same equations, you represent both subzones. But here, we clearly do not represent both zones because we are only solving for the solid structure. And so to say, we are representing the fluid flow as some external source.
Or we could represent the fluid, like the heat transfer in the fluid, with a separate system of equations and only couple them with this heat source that, like in the fluid, it would be with the minus sign, and that's all.
Exactly. If you want to deal with the fluid flow in some different energy balance equation, that's fine. In some cases, you can say maybe this heat exchanger is so short that you simply got flow of air at temperature of 50 degrees centigrade, and nothing changes in the temperature of the air. Can be like, I'm right now interested only in the porous, in the solid part. So what you need to do is, again, you need to say, first of all, what's the unit of that? It should be watts per cubic meters. Well, if we were doing everything in 2D, this would be watts per meter square. So this needs to be Q from air to solid divided by surface area of our representative element. So what's that? It's clearly heat transfer coefficient times surface area of the contact between fluid and solid. So what is it? If we approximate, it's like 5, 5, 5, 5. You want to have it more accurate, just take the computational code geometry, and you can really measure it. But first, for simplicity, this would be like, let's say, 20 for this case. Basically, it's surface area of the interface times temperature of air minus T. T meaning T at X and time represented at every point in the domain, divided by surface area of this representative element, which is 4 by 6, in our case, 24. Okay? We've been developing one of the applications for engine radiators. Maybe I made some simplifications in the geometry here, but believe me, I've been following this concept. The only thing we did differently is I think we have used our Quickersim CFD toolbox to really prepare such a two-dimensional geometry of the representative element and apply really this boundary condition to calculate flow in it, to calculate the heat conduction in each direction, and then calculate lambda x, lambda y. But believe me, taking the real numerical results and comparing it against such an estimation was within the margin of, I think, 3–4%. It was really very, very accurate. You can represent it this way. The heat source needs to be added to the system. The heat conduction parameters need to be adjusted properly to assume that you've really got some artificial porous medium material, and this one needs to be updated properly. Questions?
Maybe one comment based on a very, let's say, similar project that we did in December. The temperature in the source at the bottom is set as constant, and that's absolutely fine, providing that we make the assumption that the airflow is sufficient for the temperature to not drop or increase over the time of traveling through or that this increase is negligible. If it's not, then probably would need to take a logarithmic difference, like in a heat exchanger equation, solve a nonlinear equation, and we'll get the solution anyway.
Might be, or what you would maybe do is you would say, okay, it has got some depth in the other direction, and you need to still discretize the depth to account for this temperature variation along the flow.